So for section 4, chapter 6 in geometry, we're going to talk about inequality theorems and corollaries for one triangle. So these are some pretty wordy theorems. You're just going to have to fill in, right? Go ahead and pause and put all the words in that you need. But I'm going to talk about these first three things, the first two theorems and the corollary. But I'm not really going to read those things. I'm going to have actual examples to go with them. So when we're talking triangle here, if I made a triangle and I told you that this side, I guess I should do sides first because this first theorem is about sides of the triangle and then opposite angles, right? If I told you that this side was the shortest side, then this has to be the smallest angle in that triangle, right? And if I told you that this side was the longest side, then this angle would be the biggest angle. So both of these theorems are the same thing. It's just, does it start with angles or does it start with sides? Because if I'm going from the big angle to saying that's the biggest side, that's one theorem. But when I'm talking about going from a small side to a smaller angle, that's the other theorem. So the main thing you need to remember is what the shortcut is over here, that big is across from big, small is across from small. So whether you're starting with sides or angles, either way that's true. So those are those first two theorems. Then this corollary, right? Both of these corollaries technically. So if you need to pause for a second, go ahead and do that. But these have to do with the fact that, okay, if I had a right triangle here, right, that A, this side A, whoops, maybe I can hit that a little bit better. This side here, A, is always going to be shorter than the hypotenuse of my right triangle, side C, right? But I could pick any point, right, along B over here, side B. I could pick any point along that side and connect it, and I'd still, that yellow side would be longer than A. It has to be longer than A. The shortest distance from the point, hold on a second here, the shortest distance from this point, picking a color here that would work that I haven't used already, here's purple. Right, this point here of my triangle, the closest distance from that point to that base extended B is going to be that perpendicular altitude that we talked about in the past, right? So we actually did that, in our construction. We had a line and we had a point, and we tried to do that perpendicular line that goes through that point. And that was part of the reason to do that and make those construction marks that would tell us that, oh, hey, this perpendicular line goes through that point and the original line, but that's also the shortest distance from that point to that line. So these corollaries just tell us that. That's something that we've been using in the past already. Finally, this theorem at the end, this one's going to be a little harder to represent without a visual, because I did a visual in class for this, but the sum of the lengths of any two sides of a triangle is greater than the length of the third side. So if I had A, B, C, right, those sides of a triangle, right, the longer C gets, right, C can only get so long, right? So I could start out with something like this, where, okay, A, B, C, right? I can make C longer and longer, and all that's going to do, right, ultimately, C can end up being, right, longer, B might end up a little bit longer there, whatever. But let's assume that A and B are staying the same size. As C gets bigger and bigger, eventually what's going to happen is C is going to be the same length, right? So now I'm going to switch to my colors. C is actually going to be the same length or longer than A and B combined, and then A and B can barely reach the ends of C, and you don't have a triangle anymore. Now you just have a line, right? And if C is longer than this, then there's no way A and B can connect to each other. So the whole idea of this last theorem is that, logically speaking, if you're going to have a triangle, you're going to have to have the two shortest sides add up to something bigger than the longest side. So there's a little bit of shorthand in here, right? The two short sides must add up to more than the third side. That's what this theorem's all about. Otherwise, in practice, doing this for all the examples in your notes is pretty simple, right? So I'm going to start out with these up here. These are all just yes, no's, right? If I take the two shortest and I add them up, as long as the total is bigger than 10, yes, this could be a triangle, right? I could definitely make that triangle. The two shortest added up, it's 7. That is not bigger than 8, so no, this cannot be a triangle. So you can try and do these other three. If you want to pause real quick, you can go ahead and do that. But otherwise, 5 and 6 add up to 11, definitely bigger than the other 6, so yes, this could be a triangle. 4 and 2 add up to 6. 6 is equal to 6, not bigger than 6, so no, you can't make a triangle with that. That's that exact situation we were talking about before here, where all of the sides overlap with each other and you just have a line. You can't have a actual triangle in that case, right? Can't get a polygon in that case. Otherwise, the last example, 2.5 plus 3.1, that would be like a 5.6. 5.6 is just bigger than 5, so yes, that would work. Otherwise, these next few examples, a little weird, but same idea, right? What would have to be the length of that third side? Well, I don't know what the exact length is, but I know some bounds, right? The smallest that length could be, right? You have to add up that length and 2, some number I don't know, plus 2 would have to be bigger than 6. Now, that number could be anything bigger than 4, right? Because 2 plus 4 is 6, so I'm going to use an inequality here. 4 is less than x, x being my third side, but it has to be smaller than 2 plus 6, which is 8. So x can't be bigger than 8. X can't be smaller than 4. It has to be in between 4 and 8 for this to work. Basically, what you do is you take a and you subtract b, assuming a is bigger than b. So 6 minus 2 gives you the lower bound. And then you do a plus b to get your upper bound. 6 plus 2 is 8. So you're going to do the same thing on the next few examples. You can try that on your own, or you can pause and do whatever you need to do. But 8 plus 7 is 15, so that's my lower bound, right? X has to be bigger than 7, or this could not be a triangle. But 8 plus 15 is 23. So the biggest that third side could be is 23, right? It can't be that big, excuse me. Otherwise, 15 plus 8 would not quite make the cut. So again, you do 16 minus 14. Smallest it could be is 2. X has to be bigger than 2, excuse me. And then X has to be smaller than, add them together, 30. So there's examples like that on the worksheet. You should be able to do that pretty easy. These examples with the first theorems, right, should be pretty simple. It's not supposed to be hard. Find the longest side. That's going to give you the largest angle, opposite of it. So the largest angle is angle 3. The smallest angle is going to be opposite of the smallest side. So smallest angle is angle 2. Angle 1 is just in between those things. So which segment would be the longest? First, I do technically need to know what this third angle is, so I have to do a little triangle math. You know it would need to be 30 degrees to add to 70 and 80 to make 180 total. So that is officially the smallest angle. So this side opposite that 30 is going to be my shortest side. AC would be my shortest side. Whereas obviously 80 is my largest angle, so the side opposite of that would be the longest. So not supposed to be a terribly hard section. I know those theorems that you had to fill in were pretty wordy, but they're actually pretty easy to use.